A couple of students requested that I provide another video to help out with the second lab, the period of the pendulum. So this video will essentially go through the data that was collected, how we collected the data, and then how do you analyze the data to get some results and work out a percent error. So just as a quick recap, the period of a pendulum lab was about trying to figure out what can affect the time it takes a pendulum to swing. If you don't remember, a pendulum was just a simple mechanism. In this case, we're using a very small angle where we have like a string and we attach that string to a little bob. We call that a bob. And there's a pivot at the top. And with the pendulum, when you release it at a low angle from the vertical, the pendulum swings back and forth, right? And one of the really helpful things about how a pendulum moves is that this back and forth motion, assuming we keep the pendulum the same, keeps the same time to go back and forth. The time it takes to go from one side of the swing back to the original part of the swing we call the period. So the question of the lab was what can we change about the pendulum in order to make the period change? What will make the period get bigger, the time to swing back and forth get bigger, or make the period get smaller, right? Faster swinging back and forth. And in this lab, what we wound up coming to was that there are two variables that we could manipulate to examine. Right, so the first one we wanted to check out was what would happen if we changed the mass. Right, we tried to increase the mass and see if that made the pendulum swing back and forth. And then the second experiment was changing the length. Right, does changing the length change, how quickly it swings back and forth? Spoiler alert. Theory for the period of the pendulum says that the period of a pendulum should be equal to 2 times the pi times the square root of the length of the pendulum divided by the mass. Oh, no, I'm totally divided by g, not the mass. It's been a long day. So as I was saying, right, the period of the pendulum is equal to 2 pi times the square root of L over g. So essentially what can make the pendulum swing faster is if we shorten this, string, this number would go down, which means the period would go down. I would be swinging back and forth faster. If we lengthen the string, we would see this number go up, which would make the period go up, and that would make a longer swing back and forth. The only thing in theory, the only other thing in theory that could change the period of a pendulum would be to change the g, which we've talked about now as the gravitational field strength or acceleration due to gravity, depending on how it's presented. But basically, the only way you can make the pendulum swing differently would be if you brought it to like a different planet or really high above the Earth, right? Now, our task is to see did our experiment match up with what the theory expects. So we're going to we're going to graph these two sets of data to see, what does the trend show us in terms of, which one has an effect. Theory says it should be the length, right? And we're going to see in reality. Now, I haven't touched this data before. One of my students was kind enough to send me the data from the lab, so I don't know if this is going to be great data or not, but we'll talk about it and then get some, percent error, see if it matches what the theory says, right? One little note before we continue. This period only applies if we assume that the angle is a small angle. It's called a small angle approximation. It's approximately somewhere under 8 degrees of swing. If you swing it with like 10 degrees, you're still okay. But theoretically, it's supposed to be less than 8 degrees of swing. All right, without any further ado, let's graph the data and just look at the graphs. Now, honestly, the graphing part is the easiest part of this lab, right? So if we're looking at, we want to check how does mass versus time. Now you can see in this case, the student listed this data out, they have the length in centimeters, the angle in degrees, I'm assuming, right? It probably put it in degrees, right? Degrees. They put the mass in grams, right? So that's 4.8 grams. And then they gave a time in seconds. Now, thing to note here, this was the time for in seconds for 10 swings, right? Part of how we measured the period in order to make sure we measured it well was we timed 10 back and forth swings to figure out the total for 10 swings. And then if we want just one swing, we took this number and then divided it by 10. And this time here, you can see we took 11.215 divided by 10 gives you 1.121. That's what happened in this case. So this time is the time for one swing, which we'll call the period. Right? The period is the time for one swing forward and back. Right? That's one swing. Okay, so what we want to graph is we want to see does the mass affect the period, right? Now, one thing we should get from the beginning is we should use the standard mass. The standard mass is not grams for typically in physics. What I might do is I might add another column. If you didn't see what I did there, you can just right click on the column, go to insert, and it just adds another column. For those of you on a Google spreadsheet, might be a little different. I'm doing it in Excel because it just has some easier tools and I can draw things. But they should be somewhat similar in Google Sheets or if you use Microsoft Excel. Anyway, so we want the mass in kilograms, kg, just to be on the safe, just to be on the standard of mass we use in the course. To turn from grams to kilograms, it's pretty straightforward. We take our grams and we divide by 1,000. Now you could take out a calculator and do that, but in this case I'm just going to put an equal sign to tell the spreadsheet I'm going to do math, and I'm going to click on the box that I want to divide by 1,000. Then I backslash to show divide. I type in 1,000, and there you go. That's how many kilograms of mass, right? So what do we want here? We want period on the y-axis, and we want the period on the y-axis, we want mass on the x-axis. So whenever we graph something in Excel, we want to have two columns, an x column and a y column. And the x column is going to be, in this case, the thing that we're changing, which is the mass, right? That's the independent variable. So I'll put that in the x column. It changed to 0. The thing is, because it's a dependent scale, it's like taking that number divided by 1,000. When you move it like this, you want to go and paste the special. You don't want to just paste the formula. So specifically, you want to paste just the values, right? Paste the values. So these are just the values. If you copy and paste directly, sometimes you'll get this issue because this guy is C3 divided by 1,000. When it moves over here, it looks in this box right next to it, tries to divide it by 1,000. That's why it got 0 when we showed it the first time. So this is our x values, and they were in the mass, right? That was the mass in kg. And our y values is going to be the period, and that's going to be measured in seconds. And we'll just copy the period column, copy, paste it, basis values, right? And then to make a graph, highlight both data columns, although I'm just going to highlight these two to show this is just the axes labels for these two sets of data. Then once I've highlighted the data, I right click. Actually, I don't need to right click. I can just go up here to insert, right? And it's the same thing in Google Sheets if I'm not mistaken. Insert, charts, scatter plot, and oddly enough, we actually have what looks like a decreasing a trend, which is unusual. We're not supposed to see a drop in the period this much. Why is it so much different? Well, let's consider, right? If we took the average value here, let's see the equals to the average. So this equals our average values, right? let's take the average of this, right, all the periods. We get 1.09. So let's see how far different these numbers are from the average. So this guy, if we want to get a percent difference, right, let's think of this as a percent, right? How do we get a percent difference from the average? That's going to be equal to, you know what I'm going to do? I don't want to change this. I want this number to be important to me. So I'm going to name this cell. We're going to call this average, right? And then in this case, right, I'm going to set this as equal to, take this value minus the average, right, of all the values. And then we're going to divide that by the average value to just get a percent difference from the average. So this guy's 2%, positive 2%, and down to here it looks like negative 2%. So it looks like there's some symmetry in here, which there should be some symmetry in here. But the difference between the maximum value and the minimum value is only 2% difference than the average. So I think part of our problem here is our scale. So let's take a look at this guy and change our scale a little bit, right? See, because this scale starts at 1.07, shows to the maximum. Let's look at it from 0 so we can kind of compare it against 0. And to do that, we're going to format the axes. The bounds, the minimum, I'm going to set to 0, right? And then the units will leave that as is, and hopefully it should just now you can see it, right? This is what you would expect, right? That if the mass is changing, the period is staying at about the same level throughout the whole thing. And if I plotted a trend line through this, which you can do, right click, add a trend line, we can see it's tilted a little bit lower, but the fact is it's not very much different. And this difference could be explained by possibly we got a little biased in our results. Like maybe we thought it, or we didn't maybe have it at exactly the same length every single time. Because remember the equation for this one is the period is supposed to be 2 pi times the square root of L over G, right? And when we look at this, right, maybe what happened was they were shortening the string a little bit when they were placing it. That's one possibility, right? Now this graph, we should title it, obviously. This is period versus mass. And in this case, we also want to tune it up a little bit. I would like to have chart design. We're going to pick a chart design that's going to look nicer. We want a chart design that gives us axes labels. That's what we want. Quick layout's usually helpful. There we go. Right, quick layout's good. And yeah, that one's pretty good, right? So I'll just move all this data over here for later, right? And then this bottom title was the mass in kilograms. Mass in kilograms. And the side table over here was the period, right? Period in seconds, right? So now we can see the mass versus period graph. Again, I suspect what probably happened here is we made some kind of we kind of slightly did, we probably either shortened it or lengthened it accidentally as we were doing the data. That's my guess. Hard to tell exactly. There's also some general error in here, but the fact that it's getting a little lower every single time, that suggests to me that when we replaced the mass and we replaced it back onto the string, we were shortening it just a little bit each time, right? That would do it. All right, let's compare against the other set of data now. We have period versus mass. We want the same chart, but this time I want, we're going to keep the mass is going to stay the same. And what we want instead of mass, we want periods. So what I'm going to do, instead of mass, we're going to use length, right? So we can see here the length. Now we're going to change the length from being in centimeters to the standard. And the length that's standard should be measured in meters. So to turn from centimeters to meters, we hit equal sign, click on the box, divide by 100, and this is 32 centimeters, the same thing as 0.32 meters. Check it all through. Now we got the length. Now we can check the period. Again, I'm going to just copy and paste these guys, right? Copy, come down here, fix this, yeah? Because that's what it is. It's the same stuff. Period in seconds. And this is the period for 10 cycles. This is the period for 1 cycle. So again, I'm going to do the same trick over here. I'm going to just get the x-axis. The x-axis in this case is the length in meters. So I'm going to copy the length in meters, and I'm going to paste it down here. Values, right? And then we're going to take the time in seconds. We're going to copy it, paste this down here, time in seconds, right? And then we want to do the same trick. We want to get the, let's just open this up so we can see it a little better. If you ever have a situation where they're not big enough, one trick you can do is you can kind of stretch, although for some reason it's being uncooperative, of course. We can usually double click on these little boundaries. There it goes, right? And it opens up to fit what you want, right? So we want the, and I'm just going to change it so it says period in seconds, like so, right? And then I'll tighten it up again so it's fits, right? Length and period. So first we did the period versus the mass. Now we're going to do the period versus the length. So we have our x is length, we have our y is period. I highlight both, go to insert, go to charts, and hopefully the data looks a little better, we'll see. And in this case we've got a scatter plot that shows a increase. And you can see in this case it's a bigger, see how it's a bigger upward trend here? Now, one of the weirdness about this whole thing is that it's not a linear trend between the length and the period. Because if you remember, right, the equation is period is equal to 2 pi times the square root of L over G. So this trend here is not a straight line. It actually curves a little bit. And I suspect if our students who collected the data had shortened this even more, they would have seen a much stronger decrease. It would form like a curve. That's generally what happens with this. If we plot a trend line through this, right? Add a trend line, but let's use a power trend line because it's like raised to a power, and look at the equation on the chart. You can see, if you know a little bit of mathematics, that the chart has a value in this case, and this is, let's just make sure we're labeling it right. This is period versus length, right? If we look at the period versus length in this case, you can see that it's raised to the 0.58 power, right? 0.5 is like raising to the half power. And if you know a little bit about mathematics, when you raise a number to the half power, that is the same thing as taking the square root. So this is why you know that equation is what it is. Now I suspect there is some error in here. You can see how like the data points aren't perfectly lining up with the trend we predicted. I really would have recommended to get a better set of data here. We probably should have done at least 10 trials like I kind of recommended, but you know, you have only one period sometime in class, so you might as well, you know, do as whatever you can. So this gives us at least the idea that we might be on the right track because the equation matches what we would expect. So let's fix this guy a little bit. We want to change, we want to do the same thing. We want to have a nice format to our chart. So we go to chart design in Excel. There's similar systems in Google Spreadsheets, but I think sometimes Google Sheets is even faster because if you highlight length and period, sometimes they auto do the axes. We just have to do a little bit more work in this case. So, okay. And of course, this default switches it to, you probably can't see it, but this default switched it to a linear one. So we're just going to format the trend line, make it a power trend line, so you can see that it's a square root relationship, right? And on the x-axis, it was length in meters. And on the y-axis, it was the period in seconds, right? So now you can see, right? And looking at the chart, you can see this, the period versus length, there's a clear upward trend. Even if we don't get the full curve, you can see there's a clear upward trend in the data set. In mass, you might notice a slight decrease or slight increase, but the odds are it's probably that when you were resetting your pendulum every time, you probably accidentally got it a little tighter, not even intentionally, you probably tightened it up a little bit. That's probably the reason why you would see a decrease in the period, right? Most likely. Okay, so we got period, we got mass. These are the two graphs that you have to have for the lab report. You could just copy and paste these right over into your Google Doc when you do this in Google Sheets. The last thing we want to do is we want to get a percent error, right? So for a percent error, right, I'll get rid of that. What we're going to do is we're going to just use the equation that we have over here, right? The equation hiding behind this graph, right? We want to use that the period is supposed to be 2 times pi times the square root of L over G. So let's do that for each one of these trials. Figure out what the period is supposed to be. So this is this column is the measured, oh, of course capitalized, measured. And then this was the theoretical, right? That's a theoretical period. So we'll compare the two, right? I'm going to just copy, paste, and paste, right? Measured in theory. Measured we already have. Now we just need the theory. Now to do this, one thing we notice that in this equation, there's no m. So that's not what we need. To find the theoretical period, we're going to go over here and we're going to look at the length. You should have written down the length as you did this. And for this case, the entire length the whole time was 0.33. So we should see that this period should stay the same, is going to be the same theoretical period the whole time. So 0.33, 0.33, 0.33, 0.33, 0.33, right? Notice I didn't write 33. That's centimeters. This has to be the length in meters. For the theory to work, you have to be in meters, and you have to be in kilograms. But I mean, it's not going to matter. But this has to be in meters. So let's do it. We're going to write an equation to find the theoretical period. Step 1, I put an equal sign, and then I'm going to just put this equation, but I'm going to write it into the spreadsheet. So I'm going to put 2, because it's the 2, obviously, right? Then we're going to put a little star for multiply. Now, pi is tricky, but in a spreadsheet, if you type pi, see how it says returns the value of pi? And then you open parentheses and close parentheses. And now the spreadsheet knows that they're going to take 2 times pi. Then it's going to multiply it by the next part. To get the square root, in a spreadsheet, you type SQRT for square root. You open parentheses for what you're square rooting. In this case, I'm going to take the length that's in that column, and I'm going to divide it by the G value, which is 9.81, theoretically in New York, right? So just to recap, 2, pi, square root, because we're square rooting all this stuff, the length, which is sitting here in the column, divided by G, which is 9.81. Hit enter, and although I don't know why this guy should not be percentage. Oh, I know why, because we had it formatted as a percentage before. Let's switch it back to regular numbers, right? So the theory says it should be 1.15, and for every trial, it's supposed to be 1.15. We actually found 1.12, 1.11, 1.09. We started deviating from theory, but the first trial was pretty good, right? First trial was close to the theory. Why did we deviate? That's a good question. it looks like we added some more mass as we went down. What might have caused this? Huh. It's a tricky one. You know, I suspect we might have been retying it a little longer each time because it's going to be a little different, right? So let's find out what the percent difference is. To get the difference, right? To get percent difference, to get the percent difference, it's pretty straightforward. You're going to take the value you measured. This was the measured value. Subtract it, the actual value, the theoretical value that we were wanting, right? Put that in parentheses. We're just going to put that in parentheses because we want to do that subtraction first. And then we divide it by the theoretical value to figure out what it's actually the percent error, if you want to be, this is percent error. Percent error, right? Do it again, right? Equal sign. Take the measured value, subtract the theoretical value, put that in parentheses, and then we divide it by the theoretical value, right? So the percent error, not so bad, right? We're a little under. And I'll set as percentage. 3%, not bad. It seems like we started getting worse the further on we go. So first try was pretty good, but also I kind of think another possible reason why this error started increasing, it could be that our intuition says that the heavier it is, it should be more periods. So like our brain might naturally kind of want to delay the time to see what we expect. Bias, even in something as simple as measuring a time, is a real thing. If your brain thinks it should take longer for something to swing back and forth, you might physically have a delay in your reaction time, right? And that would cause this percent error to occur. Especially a larger percent error means there's something like that could have possibly happened. The only way we could have avoided this would be if, like, for each one of these trials, 3 people made the measurement at the same time, perhaps, right? And then we took an average. That might have been a better way of doing this, right? All right, let's do the same thing down here, right? And the fact is, we've already done most of the legwork here. What I'm going to do is I'm going to just take the same function, the theoretical function that we made for here. I'm going to copy, and then I'm going to paste it down here. Now you'll notice it's saying 0. The reason why it says 0 is because if you look at the function, this box is looking in this box to find the length. But the length is not there in this one, it's over here. So what you have to do, you literally just drag it over and say you're not going to do Q11 or O11. You're now going to do P11. And then when we hit enter, it should fix itself, right? So the theory should have been 0.13. We got 0.09, a little off, but we're going to do it for the rest of them, right? So I'm going to drag down that function, repeating it. You just click on the corner and drag it down. Same in Google Sheets. And then there you go, right? And you can see it's not that far off from each other, right? To get the percent error, since I already did the same, this is now identical to the column above. I'm going to copy that and then paste. Heck, I'll just copy both of this. That way I can, have the title too, right? 4% error here and dragging it down. You can see we got a little more error down here. Why do we have a little more error? I mean, look, this is not bad. I would say that, grading this, as long as you're under 10%, you're probably fine. It's a tough one to do if you're only doing one trial really quickly and you're not really, maybe we swung it too far. That's one possibility. Or maybe somebody missed a count. That could cause it too, right? But that's the general idea. So recap, right? What do you have to do for this lab? You have to make the 2 graphs, one for period versus mass, keep them in the standard, one period versus length. Now, if you've done this properly, theoretically, mass should stay about the same. Length, you should see an increase if you've done it, according to the theory, right? Unless you've, broken physics and found some brand new discovery. I'd love to see it repeated, but yeah, right. You should see the length increases with the period increases with the length. Once you've graphed the data, you want to find the theoretical period using the equation period is equal to 2 times pi times the square root of L over G. You put down the period, and then we want a percent error. Now, at the end of the day, you should have an average percent error for both. Average, average. And the nice thing is in the spreadsheet, so let's just call it average error, right? Average error, right? We just put an equal sign, type the word average, average, it's right there. Pick this one, right? Pick average. Oh, not that average, not the word average. Average. I'm just going to type it. Average. I'm going to put an open parentheses, and I'm just going to highlight the numbers I want to take an average of. So it's all these values first. What is this? Average, and then all these values. Close parentheses. Then hit enter. So the average error for my mass versus, mass versus period versus mass trial was 5%. And then for the period versus length trial in this case equals, we'll just do the same. I'm just going to copy because it's just easier just to copy the one you did there and paste it right down there, and boom, that's now the average error for the period versus the length. Yeah? Hopefully this was helpful and should give you everything you need to do to analyze the data from the Pendulum lab.